solution, the next part of solution to the midterm. We already did half of it, and I want to make it closer. So we already derived, this is the control volume, and we put all the, see here, we put all the actual loads, the pressure loads and inertial loads, opposite direction, the weight, gravity, unknowns here, and then you did actually write the equation just like that. And then we said if we find this bunch of m dots and pressure, all I need to substitute here just subject to statics and form reactions. That's what we did. Now, we found VD according to this equation, you get VD, and then from that, you get, in fact, let me write it, but before I want to do that, one thing I want to make a note about Bernoulli equation. So the way of doing Bernoulli equation, we started with momentum. So we had this equation, partial T, rho V, dV, plus surface integral, rho V, v dot n, ds is equal to sum of f external. So we started with that, and then next step, we made an assumption, no shear stress. That means invisible. Right? And then from that, we also made one more assumption along a streamline. So we integrated, we did line integral of this equation dot ds from point 1 to point 2, right? So if you consider your flow like this, tubes, right? Let's say you have a flow like that, right? So pick one of these streamlines, that's what I did, and integrate this equation through line integral from point 1 and 2. So from here 1 to point 2. And this is your ds. And we showed that you get this equation, P1 from the momentum, plus 1/2 rho V1 squared plus rho G Z1 is equal to P2 plus 1/2 of rho V2 squared plus rho G Z2. Right? Now you can call this C a constant, right? That means, look at this constant. It says that this constant is always same as long as you move along this particular streamline. Call this constant C1. So this value is constant along this streamline. That means P1 plus half of rho V1 squared plus rho GZ1 is equal to the same sum of these anywhere across this streamline. But if you move, if you go to another streamline, for example here, the one on the up, a little bit upward here, again, you can do this line integral, but the constant you get is C2. They are not necessarily the same. They are not necessarily the same, based on this assumption. So this is a general case. The only in general case is invisible. So if you have viscous, none of this, you can't do it. But if you have invisible, right, you can do this. But C1 and C2 are different. So what does it mean in this problem? Before I go to that application problem, I want to give you one more thing. Now, later, when we do energy, hopefully next week, we drive this equation using energy equation, a different approach. This drive based on momentum with this assumption, which is only invisible. In the energy equation, we make one more assumption. So the only assumption here is invisible. We make, if you make one more assumption, 1x more assumption, and that is irrotational. Irrotational flow. Mathematically speaking, curl of velocity is equal to 0. So what does it mean? of all, do you remember this operator in calculus, curve? Curve of a vector field, they call it curve. Do you remember that? Please answer. Do you remember, yes or no?
No.
No.
Not that
That's
terminology
what I'm
anyway.
talking about. We need to bring calculus here. This is very important thing. But look, the physical meaning of that is the rotation. Like you see this ballet dancer, the ice there, she dances on the ice and she rotates, you see? She has movement and then at some point she starts rotating. That is called rotation. And if you have rotation, this is non-zero. This is non-zero. Let's write here. This is 0. If you don't have rotation, this is non-zero. If you do not have rotation, that means you have rotation. So rotational flow in rotation. Physically speaking, that means if you put a needle with a arrowhead on top of it, in anywhere in the flow, if your arrowhead is going to rotate, it's rotational. Otherwise, it's irrotational. Now you can show that later with energy equation. If you make one more assumption that the flow is irrotational, right? Then you can get this constant equal. So C1 is equal to C2. That means, this is interesting. The constant of Bernoulli is same everywhere in the field, if the field is irrotational. But this is one more assumption, right? The basic assumption is implicit. When I give this problem to you, I just said it's implicit. But if you make one more assumption, it's irrotational, and you can say this constant is equal to the same value everywhere. What does it mean? That means you can write Bernoulli equation about any points. You don't need to look for a straight line. So the summary is this: if the flow is irrotational, you don't need to look for a straight line. You can write Bernoulli point between any points, and the result is still valid. But if your flow is only implicit but rotational, you can't write the Bernoulli equation about any 2 points. You have to find a straight line and write the Bernoulli equation. Now, for this problem, what happens here, if you, first of all, 99% of problems, they make this assumption, and it works very well in practice. So on top of implicit, they say also the flow is irrotational. So what they do, they run Bernoulli between any 2 points, and it works fine. But you need to know, these are approximations. Why? Because in the real life, when you have viscosity near wall, you have rotation near the wall, right? And also, when you have near the wall, you have viscosity, it's not implicit. So basically, you can't write Bernoulli equation near the wall or in the viscous region. So we make two assumptions: irrotational and also implicit. So now we apply this in this equation, and I'll show you why we make this assumption in order to make it closure. But you didn't have to do that in the midterm. In the midterm, you just make it very basic. You write this equation, which I saw a lot of people do that, and you just solve it. So let's go ahead and finish that. And then we go back to the slide again. So from that, you get BD is equal to do the calculation. Two times 5 So you get 3.6 meter. All right. So then from that you find m dot at this inlet, B and C. What point is that B? My hand was in the m dot B is rho B AB 1000 times BB was 2, right? Times AB by 133 squared. M dot C is equal to 1000 times 1 BC times AC by 25 squared. And M dot D is basically 1000 times VD, now we have VD, times pi, the diameter there, 75. So you have all this term, look at this equation. You need to find this two. Again, this is not necessary. So you have all this M dot, right? The only thing right now we need is PB or PC. Right, the pressure, and this is one. Now, before I do that, we want to do name quiz today. Why I explain that, because we can't wait for quiz and then we don't have time. I post the name quiz, and while we do the name quiz, I explain the rest. Attendance is not good today. Refresh your browser, see if you can see it. Quiz number 10. It's just the main quiz. I'll put the name. Now, we have MD. And the only thing I need to find in order to be able to solve for AX, AY is to find PB, you see that? And PC. In fact, if you get that, you can also solve for moment according to this. Now, how can I get PB, the pressure here? So for that, we reached with this discussion, the Bernoulli and the assumption and the So I'm going to make another drawing here. Let's draw it here because it's better in the middle. And just draw for a grade. So you have this inlet and outlet.
Just submit.
Right?
Huh? You just submit. Okay.
And this inlet.
There's another thing. You have to write your name. Oh yeah, I mean crazy.
If this is in the 1 meter per second, 2 meter per second, and this will be this outlet. So if you actually draw the streamline, that's what you get. You get something like this, and some of them they may get trapped here, right? Here. And then you get also something from that, like this. And you assume that because this is assumed, we assume that these are inlets, then what you get, the tip of this overhead is this way. Right? So what I can do at this step, I can write Bernoulli equation between these 2 points. Right? So here I have pressure here. Please do not go to the center. Okay. Then click me out. All right. So you have pressure here called a P. This is B, C, and D. This is not C. This is D. Right? So you have pressure here. You want to find pressure here, so you have just taking C, so PC plus 1/2 of rho, which is 1000, times velocity here, 1 square, plus rho times, which is 1000, times 981 G, times Z. So for Z, you can take a reference, it doesn't really matter, you can take a reference from the bottom or top, right? I take the reference from the bottom. So Z is the elevation of this midpoint there. And according to the figure, that distance is, if the entire thing is 10, minus 2 is 8. So you put 8 here, right? Times 8. So this is the sum of Bernoulli from point 1, C. Now this sum is constant over this streamline. Do you see that? It's constant over this streamline. But if I take this streamline right here, can I write this equation? No. As long as I don't have a rotational assumption. So my only assumption right now is implicit. If I have only implicit, can I change my streamline, write Bernoulli equation between this point and this point? I mean this point on this streamline and a point on another streamline. Can I write Bernoulli equation between these 2 points if I only have implicit, not irrotational? Only assumption is implicit. Can I do that? Yes or no?
No.
You can't. You see, I did like 10 minutes of derivation talking for that. I can't. Why? Because I said, when we drive, do you guys repeat the derivations when you go home?
Sometimes, yeah.
Do you guys do that? If you don't do that, this course is not like the other one. That just give me the formula number, I put it in, and you have to go through the derivation again and again and again. Now, if you go to the derivation, again, I go back to the first minute of class. You have momentum equation, and the only assumption was implicit. Then you get a sum, P plus 1/2 of rho B squared plus rho GZ. This constant is only valid across one streamline. If you change the streamline, this will change. That means you cannot say this is equal between this point and the point here. What additional assumption should I make?
Non-rotation.
Not rotation. So implicit plus irrotational. We'll see that in the energy equation. It comes from the energy equation. If I make this assumption now, can I write Bernoulli between this and this point? Yes or no?
Yes.
Yes. Now look, this assumption in rotational, as I mentioned, 99% in engineering, they make this assumption when they design things. So in fact, what they do, they can, because of this assumption, now the constant of Bernoulli is same for the entire flow. That means this head, this sum is equal to here, is equal to here, is equal to here, is equal to here. But you see that it's just approximation because you think that the flow is irrotational. Yeah.
Did you take that?
an assumption that it's irrotational for a certain section of it? And
Yeah,
then
you can do that. For example, they say near the wall, here it's obviously you have the flow is attached here, and then you have velocity here. You see that? So it goes like here to zero. It goes from some velocity to zero at the bottom. Right? So if you draw the velocity profile, it goes from velocity to zero at the bottom. So you can say here inside that envelope is irrotational. Near the wall, you have viscosity. First of all, the Bernoulli is not valid. But even if it was valid, you also have rotation. The flow particle will rotate. Why? You know that you have seen it when they have a plate, they move it, the particle gets rotated. Right? But here it's very safe. And also here, like an envelope like that. So make more assumption, irrotational, and then you can write Bernoulli about different point. And now I want to say why you need this assumption. Let's say I don't make the irrotational assumption. Let's say I only have MVC. Then I can only write Bernoulli equation between that and this one. I cannot make a Bernoulli equation between these 2 points. Why? Because they're on different streamlines. If they're on different streamlines, this head is constant is different if you only have MVC. So you can't write Bernoulli equation, right? But if it's irrotational, can you write Bernoulli?
Yeah.
Yeah. So now we will see that this point may be inlet. That means the velocity is 1 meter per second, but the other way. So if that's inlet, what happens? The flow that comes here, some part of it goes out, some part of it goes here. So again, are these equations same? If this is outlet, are these equations same?
Same what?
Same like this, the way I wrote it.
Signs will be different.
Let me ask, do I need to rewrite the equation from scratch if this V is negative?
No.
No. If you get V negative, instead of V here, which is 1 meter per second, you have VA, V, whatever point is C. For VC, you just put -1, whatever you get from Bernoulli equation, and everything should work perfectly. So it doesn't matter if you guess this is inlet, outlet, this is inlet, outlet. Whatever Bernoulli tells you, just because inlet is there, everything should work perfectly. In fact, the result you get is also consistent with physics. The only problem is, if this is outlet, the flow cannot both of them go this way. Some part, because this is going to be the only inlet, right? Some part of it has to go this way, some part of it has to go this way. Do you see that? Now, if I don't make the assumption of irrotational, I cannot write the Bernoulli between that and that. Why? Why I can't?
Say that again.
If I don't make assumption of the, let's say this is negative, pressure is negative, right? What does it mean? That means the flow is coming here. It's inlet. That means the velocity is the same 1 meter per second, but opposite direction, right? What does it mean? That means some part of this inlet is going out, one part of it is going here. Now the question is, can I write the Bernoulli equation between these 2 points?
No.
No.
No, if I have only implicit assumption. I can't. I can't. But if I make more assumption, a rotational, can I do that?
Yes.
Yes. So in this problem, it's irrotational, so that doesn't mean that if this is inlet, you have to start over. If you don't make this assumption, you have to start over. Why? Because all you can write Bernoulli between these 2 points. And also between these 2 points. You can't write Bernoulli between these two. So if you write a Bernoulli between the put number there, and your assumption is, you don't have the assumption, these equations are not consistent. So that's the reason when you see I'm writing Bernoulli between these 2 points, even though this is outlet, I'm also making this assumption of irrotation. Again, these things you have to go over and over on the derivation. That's the reason you do pretty much spend most of the time on derivation. So, yeah.
99% of the time they make that assumption. Is that because in reality the effect is so small that it's
Yeah, because what happens if this size of this was the size of like a tiny particle, then the viscosity is dominant everywhere. But look, the size of this boundary layer is so small, the region that you have viscosity and rotation, that you can consider pretty much the same geometry, but remove the skin. The skin of the viscosity, you have rotation and everything. Just skin it, right? Skin it. Then you have the same thing, object, but totally irrotational. Then in that case, you can write Bernoulli equation between any point without getting inconsistency. This could be a question in the final exam, very conceptual. So in the final exam, it's not like just give me those numbers or plug it in here. I may ask, well, I do not make the assumption of irrotational. Solve that, and then you get pressure negative here. And then can you write Bernoulli between these two without this assumption? No. Because this is going this way. There is no streamline between these two. But if we have assumption irrotational, yes, we can write Bernoulli about any point. Now we will see in the energy equation, we'll talk about that hopefully next week. Don't take anything as granted, do not memorize. Everything should go for a reason. Why? For irrotational, that constant, this constant is the same everywhere in the flow. Why? We'll prove it next week. All right? So yes, write Bernoulli between these 2 points. So this is for point C. For this point is equal to, what's the pressure here?
0.
0. Net pressure across 1/2 of 1,000 times velocity here.
3.67.
Square plus 1,000 OGZ 981 times Z. So what's your substitute Z? The height of this point. You see that from the bottom. So it's 6 minus 0.3 cosine 45. Right?
Professor, can you choose your origin for the Z to be anywhere?
Anywhere.
Okay.
Why we choose we can choose the position for origin to be anywhere? Quiz waiver? Yes?
You can make the velocity 0 at that point.
No, why can we choose the position for the origin? Here,
Because you have a z on both sides of the equation, so it's going to be just choosing a data point.
he is the one that practice at home. We go over the derivation and he understands what he's talking about. Thank you. Quiz waiver in it.
Okay. So it wouldn't be, so you're choosing the origin point, but if, like for me, I chose one of the outlets, that would be all right as long as the height was
you
4.
should get, when you see when you cancel these two, so that term, the difference will cancel out. So you get delta Z. So it doesn't matter. Take the origin as like take it to the sea level, like a million miles away. It doesn't matter because they will cancel out from both sides of the equation. All right. So when you do that, sometimes you get negative pressure here. Now you have assumption of rotational, which is very valuable. Then you don't start over because the steering line has changed. You just put here, if you get plus negative, put negative. Pressure negative, put it here. And then the end result, the force is going to give A is AY, is going to give you the exact precision result. The end result is valid. So now next section is the proper, and you see these props they use in the aviation aircraft that are low speed, subsonic, not the jet aircraft. They have a prop to generate their thrust. Right? So we want to analyze it and find a relation between the velocity difference and the thrust that it makes. So that force, you see, you know that if that prop rotates, it's going to move you forward, right? You have run that experiment. And that term, the terminology for that force is called thrust. So the relative of thrust. And usually they show it in P. Right? Now, we want to find the relation for that versus this pressure this velocity difference. Now, pay attention to that. We took a control volume that is adjusting to the airflow. So the velocity, you see this is stream. You see that? So the velocity is tangent to this output of control volume. And if you look at it in 3D, that's just like a tube. You see that? And it's surrounded everywhere, the outer, but also we exclude this object, right? This prop. So we have one control volume from here to here, and one control volume from here to here. You see that? And the third control volume is between here and here. So we have 3 control volumes. Why are we making 3 control volumes for that? Well, look, can I write Bernoulli equation between these 2 points?
No.
Well, there is I mean, when I say Bernoulli, I'm talking about implicit Bernoulli, this assumption. But look, yes, there is a streamline going here and then going up. You may say, well, I can't find this streamline. Yes, I can write Bernoulli, but look, what was the assumption? Everywhere should be implicit. What happens in the real life when the fluid comes just near that? You have viscosity. What happens if you don't have viscosity? Quiz waiver? What happens if you really
The turbine wouldn't spin.
It would spin, but it wouldn't move anything.
push anything? It will spin very well. In fact, with a little touch, it will spin forever. Because nothing is damping it. There is no viscosity. Do you see that?
No friction.
But there is no way you can generate the velocity difference. So in this case, we cannot say, well, let's say it's implicit, just like this case. The physics of this is based on viscosity at evolve, right? So the end result is, I may give questions like that conceptual. Write Bernoulli equation between this point and this point. When I say Bernoulli, in this intercommunity, because later on the energy will add energy drop and then we can write Bernoulli. Implicit, you can't, right? Because there is a viscosity here. If there is no viscosity, there is no thrust. You see that? There is no way that you can generate thrust. So that's the reason I have one control volume here that is dealing with the viscous effect. But look, what about the control volume here? Can I write Bernoulli between these 2 points in this control volume?
Yes.
Yeah. Because I'm not touching anything in this. What about these 2 points in this control volume?
Yes.
Yeah. Right? So I have 3 control volumes, and then based on the 3 control volumes, if you write equations, so these are the velocity. You see the velocity initially is small, and then when it passes, you see near this turbine, near this propeller, the velocity here inlet is same as outlet. Why? We show that, hopefully you prove it. But here the velocity is higher. So it's smaller, then you go to constant velocity, and then you go to this higher velocity in the core. So that's showing the velocity in the book. And then you start with the equations. So now, I really want to find a chance. You know, I know there are more slides. We have one for example. Probably we have one class, one for brackets. But I do not want to show you, okay, this is the end result numeric. We want to drive this. And it takes some time to drive it. In the book, it doesn't do that. So if you want to do that, you said you struggle. So that's the reason I'm trying to do it right now. So from my 3 control volumes, and I write all the equations I have with those control volumes. So one is here. One is here, just near the plate. And one is here. So let's say it's point 1, 2, 3, 4. Right, so you have pretty much same uniform velocity here, V1, V3, V4, again V4 comes here, and V2. Now, if I want to draw a control volume on this system, I wish I had a little bit of space with me. Let's put some space. So the second one is this. The last one is this. So 3, 4, 4, 2. Right? So I want to draw a 3D. Loop over the border of this system and include all your surface fluids, physical or non-physical. Well, I have pressure. I have pressure, right? P1. And then what else? This P1, A1. What else do I have? Well, the flow is coming in, right? What's the normal? This way. V dot N is negative, so this is the actual sign of the inertial term. You flip it opposite. So that's your M dot at 1, V1. Right? So you go, next step. What do I have here? You see the velocity is this way. V dot N is what? All over the top. V dot N is what?
Zero.
Do I have, you see that you have some pressure here, but they will cancel out with the bottom because it's perfectly choosing like perfectly symmetric. This is what I choose. This is not the geometry. This is not inside the tunnel. This is not the tunnel. This is what I choose as my control bottom. So you are free to make it perfectly symmetric. So there is no external load here. Then here, the velocity is this way. Normal is this way. So the actual direction of inertial force is this way. So you put opposite. M dot 3, D3. What about pressure? E3, A3, right? And then you come here, there is no external load. Body force, well, you say this is air. If you have just a huge value of propellant, like a huge one inside the sea, so this water, yes, you will get a body force, right? Which will cancel out the hydrostatic pressure bottom and top. Right? But we don't consider that here. So go to the next system. For this, you have opposite of that, pressure, E3, A3, and then opposite of that here. So the velocity goes, see the velocity here for this normal is this way. Velocity goes here, M dot V is this way, you put opposite on this, M dot 3, V3. Then nothing here, and here you have P4, A4, and then velocity is going this way, and is this way, so you put opposite here, M dot 4, A4, and B4, and nothing here, and then finally P4, put opposite here, A4, opposite here, M dot 4, B4, and nothing here, and the last thing you have here is P2, A2, and it's the other way, and then the inertial load is M dot 2, A2. So 3 systems. Now, my goal is to find a relation between the thrust and the velocities. Now, a quiz level, am I missing something in one of these 3 FEDs, and or maybe 1 thing or 2 things or 3 things, and which one? Let's say this is FED1, FED1, FED2, and FED3. What is missing here in what FED?
Most likely the weight of the propeller in FPD2. And then there's also friction that you have to worry about unless there's no friction involved.
Yeah, there is a friction that you have to worry about. Thank you. Very well. There is a friction you have to worry about. You see, do I have friction here? No. It's like far-field. Before it comes into this blade, this guy will make a lot of friction on the surface. Do I have friction here? No. But look, here, this guy, through the friction, it generates effect. So that effect is a very complicated surface integral over the entire blade. Let's put the sum on the FED. Let's call it F, or thrust. That is called thrust, T, but let's call it F. What's the direction I should put on the FED? This is the flow. It's not the blade. This is the FED for the fluid around the blade. What direction of the force that put it on it? To the?
To the left.
Right, because this blade is pushing it to the right. Now, if I wanted to take the blade as my system, what was the direction? Just like the nozzle problem we solved before. Right? Okay, now we're ready to write equations. So starting with this, let's start. Also, let's take the entire thing as a system. Let's just write it. FPD. No. So FPD 1, 2, 3, and the entire thing 4. So for FPD 4, if I write the equation of equilibrium, what do I get? This thing needs to go up. For FPD 4, I get, this is my system. Loop over the surface, so you get what? Sum of force next 0, m dot 1, E1, plus E1, A1. Right? Then you go all the way, and another thing before I write P1, A1, because we should simplify it. When you go to far field, you see not near the blade. You see near the blade, you have increasing pressure, right? Because it's just hitting the flow. What was the far field? Do I have P, the gauge pressure? What's the gauge pressure in the far field? This is the far field, huh?
Atmosphere.
Say that again?
Atmosphere pressure.
The atmosphere. So this is the gauge that I put on FPD. It's P0 plus gauge, right? P0 cancel out everywhere. So it's just a gauge. What's the gauge pressure in the far field? Say that? This is far field. This is far from the blade. What is P1? 0. What is P2?
0.
What is P3? It's just near the field, near the blade. What is that? Is that 0?
No.
No. There is some increasing pressure. You see that? And also P4, there is some increasing pressure. But in far field, it's just a gauge pressure. It's just the atmosphere pressure. So here, when I write my equation, I do not write it here. I could, and later on say this is 0. But I do not write it, I just say m dot V1 is 0. And then the next thing on the outer is just what? M dot 2V2. Positive or negative?
Negative.
Then what else? You see, all of these, look at it, they are cancelled, action, reaction, they cancel out. Do you see that? They all, you see this way, this way, they all cancel out. What else remains?
Force.
The external force. There is an external load that is act and comes from the blade because we extended the blade. That force comes from the blade. Positive or negative F? Plus F is equal to 0. Right? And now write continuity equation. Write continuity equation for the big system. What do you get? M dot 1? Positive or negative? Negative. Plus M dot 2 is equal to 0. That means these two M dots are same. So you can solve this for F and say F is equal to M dot 2 V2 minus M dot 1 V1, right? And then because these two are same according to continuity equation, put in the momentum, you get F is equal to M dot, call it M dot. V2 minus V1. So the question is, what is M dot? M dot is the same along this tube. Do you see that? Do you agree with that? So can I write M dot as M dot 3 or M dot 4? You see, all of them are same. M dot 2, M dot 3, M dot 4, conservation of math. So for that, I'll just write M dot 3, which is what? Rho V3, A3. What's the A3? The area of here. There is a blade here. What's the area of this blade? If I know the diameter of the blade, what's the area of the blade? Pi
R squared.
R squared times rho times V3. So look, the thrust equation is just simply rho times V3 times A3 times pi R squared times V2 minus V1. That means if I get V3, I do not have velocity here. I have everywhere, you see, but I do not have velocity here. If I get velocity here, then I can get the relation for the truss. Yeah.
Would you take out the A3 because the pi r squared is the area? Because it looks like you have area twice.
Yeah, thank you. I appreciate it. So this A3 here, what is that? I just write pi r squared rho, so this rho, A3, B3, and this is come from. Now I want to find B3. What should I do? Well, I can take this system and write Bernoulli equation between these 2 points, as I said. Bernoulli between 1 and 3. What do I get? P at 1 is 0 plus 1/2 rho V1 square plus, there is no elevation difference, is equal to P3, which is non-zero, plus 1/2 of rho V3 square. Elevation is also 0. What about Bernoulli equation between these 2 points? You have 1/2 of P4, 1/2 rho V4 square plus P4. There is no elevation, is equal to 1/2 of rho V2 square plus P here is also 0. So look at it. Add these 2 equations together. So if you add it together, you get 1/2 of rho V1 square plus here both sides of this 1/2 of rho V4 square plus P4 is equal to P3 plus 1/2 rho V3 square plus 1/2 of rho V2 square. So that's equation. But look, now do this. Write continuity for this system. If you write continuity for this system, we get what? M dot 3 is equal to M dot 4. And that means rho V3 A3 is equal to rho V4 A4. This row cancel out. A3 is what? A3 is equal to A4. It's just the area of the blade. So V3 is equal to V4. So that means what? You can cancel out these 2 terms. These are same. You see that? So what do you get for difference in pressure? You get P3 minus P4. From this equation, P3 bring it on the outside. P3 minus P4 is equal to 1/2 of rho V1 square minus V2 square. Right? P3 minus P4 is 1/2 of rho V1 square minus V2 square. But look, for this equation, for this system, write momentum equation. Sum of force makes 0. So what do you get? You get M3 V3 positive plus F minus M dot 4 V4, and there is plus P3 A3 minus P4 A4 is equal to 0. Look at that. So that means, put it here, that means your M dot, which is, you see, M dot 3 and 4. What's this difference? M dot 3 and 4 is 0, right? Because both of them are same here. So this 0, so you get F is equal to P4 minus P3 times both area is same, call it A. Now look, put it here. That means this equation is going to give you 1/2 rho V1 square minus V2 square is equal to P3 minus P4. So negative F over A. Now you have this equation, and then you have the initial, this equation. Compare it to here. Let me write it here. You have rho V3 times, let's call it A. V2 minus V1 is equal to N. Right? So bring this A here. Multiply by negative, so you get negative here, positive here. multiply by 8, so you get another 8 here. Now divide this together. What do we get? If you divide it together, divide it, then you get this. You get 1. V2 squared minus V1 squared is equal to f divided by f1. So there is another V3 plus V3. So what do I get? Look, expand that. What you get V3 times V2 minus V1 is equal to 1/2 of, expand that, you get V2 minus V1 times V2 plus V1. Right? It's cancelled out, so you get V3 is equal to V1 plus V2 divided by 2. Now, that is in your book, without giving you all these details. See, that's the final result. This is B. And when you get B, you just put it in a truss and you get a question for truss. For final exam, I will definitely ask things like that. So you really need to watch the video. You really need to practice. We're not gonna give this class without understanding, right? So you get this B, and then you substitute it in here for V3. You get thrust is equal to rho 1/2 of velocity in the time. The area times the velocity difference. So once you have the velocity inlet and outlet, you can find the thrust. That's what you're going to do in the lab.